In this lecture, I'll do the change of variable to spherical coordinates. I broke these lectures up into smaller sections since they got too long. And also I'll do the problem of the volume of the Earth from homework. So now again, we're taking a triple integral and we're going to change the variables. And for cylindrical coordinates, we changed we changed x, y, and z into r, theta, and z. And now for cylindrical coordinates, we're going to change x, y, and z into rho, theta, and phi. Those are our spherical coordinates. And here's the transformations are right here, writing, as usual, the old variables in terms of the new. Now in the homework, I want you to work out this determinant for practice, I guess. But we have to get the Jacobian for that transformation, and that will be the matrix of all these partial derivatives. And let's see if this should be fairly obvious. Let's look at the last line. Z equals rho cosine phi. So when I take the partial with respect to rho, I just get the cosine of phi. When I take the partial with respect to phi, I get rho sine phi. And when we take the partial with respect to theta, I get 0 because z doesn't depend on theta. I think I have a sign error here. There we go. Okay, and as far as the other two lines, let me erase that screen and write what's going on there. You're taking partial derivatives of x equals rho sine phi cosine theta. So this is the partial with respect to r, here's a partial with respect to phi, and here's a partial with respect to theta. You need to work out this determinant. After you work out the determinant, no, I did them in the other order, I'm sorry. This was the partial with respect to r, this is the partial with respect to phi, and this is the partial with respect to theta. Okay, anyway, you can work up your own matrix, it's not a big deal. Just look at the original transformation, which would be rho sine phi sine theta, and then of course z equals rho cosine phi. Get a matrix of partial derivatives, then take the determinant. Once you take this determinant, there's lots and lots of terms. Make liberal use of sine squared plus cosine squared equals 1, and all sorts of things fall out. And here is the answer. The answer is rho squared sine phi. That's the Jacobian. Remember, the Jacobian for cylindrical coordinates and polar coordinates was just r. Here it's rho squared sine phi. So when you make the transformation from Cartesian into cylindrical, you rewrite the function in terms of the new coordinates, spherical coordinates. The dx, dy, dz are replaced with the Jacobian, rho squared sine phi, d rho, d theta, d phi. Also in the homework, I asked you to show the volume element, this is the volume element for integration in spherical coordinates. It's similar to the one for polar coordinates. Rho, which is a radial component, changes. It's shown right here, but it changes. You can look at it down here. It doesn't matter where you look at it. This is just change in rho. Now when you look at the others, there's this is a volume element, so it has three sides. You have this side along here, which is not a straight line. Okay, it is an arc of a circle. So it's rho times d phi. Okay, rho delta phi. That would be this little part right here. If you just looked at this front part, this front face of it, that's the same as polar coordinates, except instead of theta you have phi. So now you have two terms of that are going to be multiplied together to give you that volume element. Remember previously you had dx, dy, dz in Cartesian because the volume is a little box. And here you have this wedge-shaped volume. So we have delta rho, that's for the change in radius. Then we've multiplied that by rho delta phi. And now there's another piece of this volume, and that's the side, these side elements. Their lengths obtained by projecting them onto the xy plane. So to project them down, you would need sine phi, and then again you have the arc of a circle times delta theta. So here's the last term. It's rho sine phi d theta. Let me write that all over again for you. The whole idea is that you're changing the rectangular box-like element in Cartesian coordinates dx, dy, dz into this wedge-shaped three-dimensional volume element. And I'm going to multiply the sides together, the lengths of the sides. The side in the radial direction, that's the side right here. Its length is delta rho. And now look in, or d rho. Look in the in this plane, the length of that is rho delta phi. And this side is computed down here. Its length shown down here is rho sine phi d theta, or delta theta. You put that all together. Here is, you have a rho and a rho here, so you get rho squared sine phi d rho d theta d phi. And my pen ran out of room. Don't worry, I've got it typed somewhere. Here it is, rho squared sine phi. So that's the Jacobian. When you put all this together, you get that volume element, rho squared sine phi d rho d theta d phi. Let's use this to calculate the volume of a sphere. So if you want to write it in Cartesian coordinates, it is this unwieldy integral, triple integral, in terms of dx, dy, dz. Remember, you would obtain these limits by picking one variable to have constant limits. In this case, it would have been the x, got picked for that. Then you project the figure into the xy plane and find the limits for y in terms of x, because that's the only remaining integral, beyond it. And then you find the limits in z, and you do those for x and y. You do it by drawing lines through the figure and finding where it enters the region and leaves the region. And here's your limits in z, and remember, it can depend on the other two variables, x and y, and it does, but the y can only depend on the x, and that's the only dependence it has. So instead of integrating in Cartesian coordinates, we'll change to spherical coordinates. And here, let me erase that. Here's the transformation. We've taken the xyz Cartesian coordinate formulation and we move to spherical. To move to spherical, you take the function, you rewrite it in terms of r, theta, and phi. Then the dx, dy, dz get replaced by the Jacobian, rho squared sine phi times d rho d theta d phi. In this case, the function is just 1. There's no function here. Well, you could put imaginary function 1 or invisible. There's no change with the change of variables, so that's the same. So I take the dx, dy, dz, and I write it in terms of rho squared sine phi, which is the Jacobian, d rho d theta d phi. What is rho doing? It's going from 0 out to the edge of the sphere. So that's why its limits are 0 to r. Theta goes all the way around 0 to 2 pi, and phi, of course, is restricted between 0 and pi. So I carry out the integral with respect to rho, and I get r cubed over 3, because I had it started with the rho squared. Oh, the wrong one got left. I apologize for this, but sometimes I get tired of remaking these videos like 100 million times. Okay, there you go. Fix that. So now I want to integrate with respect to theta from 0 to 2 pi, and of course the answer there is just going to be the 2 pi. Now I have to integrate sine phi from 0 to pi. Of course, get minus cosine phi, evaluated from pi from 0 to pi. And here's the answer. 4/3 pi r cubed, which indeed is the volume of the sphere. It required this Jacobian to get the answer. Now I'm going to look at that homework problem for calculating the volume of the Earth. And it involves two change of variables. And the first change of variable is taking the sphere, that sphere, which is, changing the ellipsoid, which is the Earth, and changing it into a sphere. So here's the change of variable, and it's given to you with some numbers. So the old variables were x, y, and z. The new variable x is a times u, y is b times v, and z is c times w. Here is the expression for the ellipsoid. X squared over a squared plus y squared over b squared plus z squared over c squared equals 1. To show that this becomes a sphere, I'm going to substitute this transformation into there. So of course in the numerator I have a squared u, and the a's cancel, b squared, and the b squares cancel, and same with the w and the c. And I end up with a squared plus b squared plus w squared equals 1, and that is the equation for a sphere. Now let's look at the Jacobian for this transformation. Remember, it will be the determinant of the matrix of all the partial derivatives. Let me write again here for you what the transformation was. X equals AU, which is why you only have an A here and nothing with V and W. Y equals BV, so that's where the B comes from in the second row, which are the derivatives of Y. And Z equals CW, and so you end up with a C here. Taking the determinant, you just get ABC, A times B times C. That's your Jacobian. So now I'm trying to calculate the volume. So this is basically what I'm trying to do. So I write a little template for myself here. Okay, the function is just rewritten in terms of UVW. Well, the function's 1. I'm just looking for the volume, so there's no function to change. No change there. The dx dy dz becomes the Jacobian times du dv dw. But the Jacobian was ABC. So here's the integral. This is the integral over the ellipse. I'm not putting any, you don't need any limits here because you're not going to carry out this integral. And now, with this transformation, it becomes ABC, which is the Jacobian, times du dv dw. And this is over the circle or the sphere. U squared plus v squared plus w squared is less than or equal to 1. But this will still be a complicated integral to carry out, so I'm going to transform this into spherical coordinates. So here is the volume of a sphere. We did that before, so we're going to convert from spherical coordinates. So now I have the UVW, and I want to go to spherical coordinates. Here's the Jacobian for the spherical coordinates, rho squared sine phi. That has to go into the new equation, followed by d rho, d theta, d phi. Right, the first term, we had ABC, that was constant. Here's my original formulation right here. The ABC is just a constant. I can write this on the outside, and then I will just have to change du dv dw into sine squared, rho squared sine phi, d phi, d theta, d phi. Of course, I know what the answer to that is. This is just the volume of the sphere. You can carry that out like I did in the previous example. We're calculating the volume of the sphere. Just take these different integrals, and this is a 1 here, okay, and then the answer is multiplied by ABC. So that's basically how to do the problem for the volume of the Earth when the Earth is considered an ellipsoid.